about to report the composition of the perovskite solar cell. This photo shows the cell efficiency records of the perovskite solar cell. Perovskite solar cells have shown potentially both in rapid efficiency improvement from 2.2 in 2006 to the latest record of 20.1 in 2014, and in cheap material and manufacturing cost. High and rapid improvement efficiencies as well as low potential material and processing costs are not the only advantages of perovskite solar cells. Flexibility, semi-transparency, tailored form factors, thin, high weight, and other value proposition of perovskite solar cell. This graph shows the efficiency record of the generation of solar cell. Here is the line graph of the first generation silicon, and here is the line graph of the second generation thin films, and here is the perovskite third generation, with now having a 20.1 efficiency rate, can now or almost the same with the traditional silicon. So what are perovskites? Perovskite is a type of mineral that was first found in the Ural Mountains and named after Lev Perovsky, who was the founder of the Russian Geographical Society. And a perovskite structure is any compound that has the same structure as the perovskite mineral. Perovskite mineral is formed of calcium, titanium, and oxygen in the form of CaTiO3. Meanwhile, perovskite structure is anything that has the generic form AbX3 and has the same crystallographic structure as the perovskite mineral. In this slide, we can see a structure of a perovskite with a chemical formula AbX3. We can see a large molecular organic cation type A, which is a metal ammonium in the center of the cube. And in the corners of the are then occupied by a smaller atom B, which is an organic cation that is usually lead. And in the faces of the cube are occupied by smaller atom X. This atom X is slightly smaller than halogen anion, which is usually a chloride or iodide. Note that these two structures are equivalent. The left side structure is drawn so that the atom B is at the center position, while on the right side structure is drawn so that the atom A is at the center position, and the lines are guide to represent crystal orientation.
I'm Angelica Calot, and I'm going to discuss the structure of the perovskite solar cell. Before we discuss the structure of the perovskite solar cell, let us know first how the solar cell works. A solar cell uses a semiconductor to generate electricity. When light gets absorbed by a semiconductor, the crystal negatively charged electrons surrounding the atoms in the crystal lattice absorbs the energy of photons and are promoted to conductive electronic states in the crystal known as the conduction bond. In turn, a conductive positive charge, called the hole, is left behind at the lower energy state of the crystal known as the valence bond. If positive and negative charges are collected at the opposite electrodes in the solar cell, known as the cathode and anode, then the charges can conduct electric current through an external circuit. At the same time, the potential energy difference between the positive and negative charges that are collected in the cathode and anode results in a voltage which allows the solar cell to drive current through a load in the external circuit to generate power. And that's how the solar cell works. Next, the basic structure of a photovoltaic solar cell. There are three main parts of a photovoltaic solar cell: the light absorber, carrier collector or collectors, and the metal contacts. Absorber, it converts photons to electrons and holes. While in carrier collector or collectors, it captures the carriers or the electrons and holes. Lastly, the metal contacts transfer the carriers to the circuit. Now I'm going to discuss the structure of the perovskite solar cell. The perovskite solar cell consists of three layers that are between the metal contacts. The structure of the perovskite solar cell starts with a glass substrate. The transparent contact is made up of fluorine-doped dioxide, known as the FTO. Next to FTO is a layer of titanium dioxide, which is an N-type semiconductor that is used to conduct electrons. These first two layers make up the end of the solar cell. On top of that, we deposit a metal ammonium lead trihalide perovskite. The perovskite is a semiconducting crystal that absorbs sunlight to generate electrons and holes, which are then transported down to the anode of electron and up to the cathode of the holes. Next to that layer is a small molecule called spiromethat. Spiromethat is a p-type layer that is used to conduct holes. And lastly is a contact made of gold. The spiromethat gold layer makes up the cathode in the solar cell. And that is the structure of the perovskite solar cell.
Good day, I'm Fossil Camille and I'm here to discuss about the processes that perovskite solar cells undergo. Perovskite solar cells hold an advantage over traditional silicon solar cells due to the uncomplicatedness of its process. Here is an example of the silicon solar cells. Traditional silicon cells require expensive, multi-step process conducted at high temperature, which is greater than 1000 degrees Celsius, in a high vacuum in special clean room facilities. Meanwhile, the organic and inorganic perovskite solar cell material can be manufactured simply and inexpensively in a traditional lab environment by means of simpler wet chemistry techniques using low-cost laboratory equipment instead of the expensive deposition equipment common in the semiconductor industry. Here are the materials needed. Solar cells are made in tandem fashion or layer-by-layer manner on a specially coated glass support. Here are the demonstration of the fabrication of solar cell perovskite. Here are the materials. We need 2 FTO glass, titanium persecure solution, perovskite persecure solution, copper thiocyanate solution, and carbon powder. In preparing the titanium solution, we need 5 milliliters of ethanol and 0.3 milliliters of titanium isopropoxide, and lastly, 0.1 milliliters of hydrochloride acid. After combining the three together, we'll let the solution steer at a room temperature for about 10 minutes. To make the perovskite solution, we need to mix 140 mg of lead chloride and 200 mg of methylammonium iodide in 1 ml of DMF or dimethyl formamide solvent. The reaction shall be stirred at 80 Celsius until it has formed homogeneous yellow and transparent solution. Lastly, we need to prepare the copper thiocyanate solution. We need to stir 6 mg of thiocyanate powder in 1 ml of TPS or dipropyl sulfide at room temperature overnight. To know if we succeed, the final solution should look colorless and transparent. Depositing the titanium solution. We need to place FTO glass with the conductive side facing upward, and then deposit 1 drop of titanium onto each of the glass. Spread it across the surface. Place the glass piece on a hot plate facing up and at 450 degrees Celsius for about 20 minutes and let it cool down for 10 minutes. Depositing the perovskite and copper thiocyanate. Put 1 drop of perovskite solution to each glass and spread it across the glass to create a uniform, smooth film. Remove the glass piece. Place the glass piece on a hot plate and heat it to 110 degrees Celsius. Wait until the film turns completely black and let it set there for 10 minutes. After that, deposit 1 drop of copper thiocyanate and spread it quickly across the surface. Get a carbon powder and sprinkle 1 spatula full of carbon powder on the glass piece. Then cover it with another FTO glass with the conductive side downward. The last step is fabricating the solar cell. Start by placing the FTO glass with the conductive side upward. Next, we place a layer of titanium solution covering 3/4 of the FTO FTO glass. Then we cover the surface with a perovskite light-absorbing material. Next, followed by a layer of copper thiocyanide. To complete the device, we sprinkle carbon particles on the layer and close it with another FTO glass with the conductive side facing down.
I am Angeline Lepitin and I'll be reporting about the performance of a perovskite solar cell. A perovskite solar cell is a type of solar cell which includes a perovskite structural compound, most commonly a hybrid organic-inorganic lead or tin halide-based material, as the light harvesting active layer. Perovskite materials are cheap to produce and simple to manufacture. So, solar efficiencies of devices using these materials have increased from 3.8% in 2009 to 20.1% in 2015, making this the fastest advancing solar technology today. According to detailed balance analysis, the efficiency limit of perovskite solar cells is about 31%, which approaches the Shockley quasar limit or SQ limit of gallium arsenide, which is 33%. SQ limit refers to the maximum theoretical efficiency of a solar cell using P to N junction to collect power from the cell. Their high efficiencies and use of abundant inexpensive materials with a simple cell structure, low wastage, and low manufacturing cost make perovskite solar cells a commercially attractive option. Lead halide-based perovskite has been used as solar cell material. Perovskite solar cells are promising, low-cost, and highly efficient next-generation solar cells because they can be through a low-temperature process such as spin coating and generate a large amount of electricity due to high optical absorption together with the high open circuit voltage.
Rose Pianago, and I'm going to give one example of perovskite solar cell. The Department of Applied Physics of Hong Kong Polytechnic University has successfully developed efficient and long transparent perovskite solar cells and graphene electrodes. The power conversion efficiencies of this novel invention are around 12% when they are illuminated from fluorine-doped tin oxide bottom electrodes or the graphene top electrodes compared with 7% of conventional semi-transparent solar cells. Why and how graphene is turned into perovskite cell? Graphene is an ideal candidate for transparent electrodes in solar cells with high transparency, good conductivity, and potentially low cost. Firstly, the conductivity of graphene was dramatically improved by coating a thin layer of conductive polymer poly or the ethylene dioxythiophene that was also used as an adhesion layer to the perovskite active layer during the lamination process. Secondly, to further improve the efficiency of power conversion, Hong Kong Polytechnic University researcher found that by fabricating the solar cell with multi-layer chemical vapor deposition graphene as top transparent electrodes, the sheet resistance of the electrodes could be further reduced. Lastly, performance of this novel invention is further optimized by improving the contact between the top graphene electrodes and the whole transport layer of the perovskite films. So what is its advantage? Graphene and perovskite lead to inexpensive and highly efficient solar cells. A big concern for researchers was lowering costs. They claimed that their solar cells less than $0.06 per watt, which they can reckon is more than 50% reduction in the cost of silicon solar cells. They believe that the whole process is ripe for scaling up because the mechanical flexibility of the graphene enables the possibility of roll-to-roll processing.